Okay, so the topic of today's lecture is you finished your app. Somehow the marketing worked beautifully, and there's people who want to use your web app. And what does it take to support all the users who want to use it? So, what do I mean by that? What does it take to get your app used by lots of users, possibly at the same time? Because you are a startup, you've been, saving and eating your savings, and now you want to get some revenue, right? But you want to do it with good response time, because otherwise people don't stick around, and you don't get to, have recurring revenue. That's a key word for a startup. You want revenue that you can count on 3 months down the road, because when you hire people, you promise salaries 3 months down the road. And you want to do it with as few resources as possible. Okay? So that's a pretty big order. Lots of people, quick response, for free. And what this means, you want to maximize the hardware that you need to employ. Even how much that hardware has to work, because you're paying electricity, and that it all adds up. Right? It's amazing. And then the fewer machines you have, and the simpler configuration, then you reduce the maintenance resources. All that. And there's a whole lot of techniques that you can use. In fact, once I was writing this set of slides, I realized I could teach a whole course, a whole semester worth of how do you actually operate your software at scale. We're going to learn about deferred tasks, caching of various forms, application servers, load balancers, and some other cool stuff like thundering herds and other animals like that. Okay, so let's start. And by the way, I assume that some of you have seen some of this, maybe a few have seen it all. I personally have seen all this stuff only in my third web service that I built. How do you start? Let's assume you're using Rails or Django, and that puts, there's a lot there already for you. In fact, you can just run one of these commands. This is for Django, manage.py, run server. And magically, it fires this web server that listens on port 8000 maybe on your local host, and you can access already your application through a web browser. In Rails, I think you do Rails server, and it will run a WebRick, the built-in server. And what happens when you do that? Essentially, this is the application that you wrote, and there's an embedded, very tiny web server that comes with your framework. And it takes care of listening to the requests and forwarding pretty much everything to your application. And the application, through its routing tables, has to deal with separating out requests for static assets. These are HTML files, JavaScript, CSS, and requests that really need to operate your views, and those eventually, some of them go to read or write to the database. Okay? And most of the tutorials, so using Django and Ruby on Rails, this is where they end. Essentially, then they go on what you can put in your application, how to put stuff in your database, but they never take you to the next step. And this is really not enough to actually have it used. Can you tell me what are some problems that you have with this kind of setup? Some limitations.
Server, you're just running from your local computer.
Right, so you can't really expose it. But let's say you were to expose your local computer to the internet.
Well, it would need to be on all the time. You would never.
Might. Okay, yes, that's possible too. Even then, it's.
They're not built to handle a large number of requests.
Right, so they're not going to be able to handle a large number of requests. And.
To add on to that, the main thing would be your local connection.
You'd be limited by your local connection. Yeah, so I'm already going farther with this than I actually plan to even cover in this lecture, like the network pipe to the exterior. Have you noticed that this actually can be slow to respond? Because I didn't notice it initially. So let me show you. Okay, so what I have here, this is a little web service that I built, and I disabled the cache, and I run. I hope I still do. Yes, I run a Django embedded server, as in the picture, and Django is listening on port 8000, and it took here 2.93 seconds, and this is the simplest page in my web app. Why? Because I have jQuery and a bunch of other stuff, some GIF images, some CSS, and 3 seconds. That's how long it takes. Let me switch to the actual presentation. Have you noticed this? No? Okay, so the problem is that most of these servers are really built to be simple. They're not doing any concurrency. They will take one request, go figure out, load the files from disk into the application in Python or Ruby and forward it to the web server. So that's actually very, very slow.
So all you're saying is that the embedded web server is much slower than, say, an actual production web server.
Yes, but it's incredible. You might think, okay, it doesn't make a difference for me. It starts to make a difference very quickly. If you have 10 JavaScript and CSS files, it's already taking a lot. And you know when I started noticing this? Once I wrote my automated tests for the UI. Because when you're a human pressing reload, 2 seconds is something you can deal with. But when you have 100 automated tests that need to load this page, suddenly you say, well, why does it take 3 seconds to just start the test? Okay? So one thing that you've learned perhaps to do is to compress the static assets. How many of you have tried this for your projects? Okay, very few. I don't expect that you'd be optimizing it that much. So there's 2 kinds of compression that you can do. You can minify JavaScript, pack all of the JavaScript, your JavaScript with jQuery, Bootstrap, all together in one big blob, and even reduce the white space and all that. So that actually has a good effect. And you can take images, actually, and construct one big image with all of your images, like a whiteboard. And then the application loads one image and just shows different parts in different parts of the application. So that's a technique that people use to reduce icons and such. But before you go there, I want to go down another path, which is to bite the bullet and actually start using a real web server that was designed to serve web pages. Okay, so here's the setup. You install either Apache or Nginx or Lifey or some other web server, but this is not one of the toy web servers. This is really built for performance. And it installs, it's trivial to actually install even on a Mac or a Unix machine. And then you configure it to recognize all the URLs that refer to the static assets, and you tell it, deal with these directly. Because these are very good at going and finding things on disk and caching them and serving them very, very fast out of their internal cache. And then you tell them everything that doesn't match the certain URLs, send over to my application. So this is your application, and it looks almost like on the previous slide where we had the embedded server, except that this time, with just slight configurations for Rails and for Django, it's going to package your application into a process that has not an embedded server, but an application server. Okay, so what is an application server? It's a very thin layer around your application that speaks a protocol over which it receives essentially serialized HTTP requests. Okay, so remember that the HTTP requests come in text form. The headers are textual and then the body of your request. Nginx and Apache speak some of these protocols and know, and you can configure them to take all that request and package it into a blob of binary data, something that's encoded for speed of transmission and speed of decoding on this other end. And on this other end, this thin layer will decode those headers and then will invoke your views, essentially, Rails or Django. Okay? So there are many kinds of protocols here, and they all you recognize them that they end with this GI thing. So CGI was the first one that was invented from the very beginning of the web servers. And we talked about it early on in the class. CGI, what it was doing, the web server was essentially starting a brand new process with your application for every incoming request, passing it the data through headers, through environment variables, waiting for output on standard output, taking that output and responding it and killing the process. So that was the beginning of web in 92, 93 or so. This has been abandoned pretty much. So now the two that are used a lot with Python is WSGI. It's a protocol that was built for Python. And there are several implementations of this. I am using UWSGI in my project as the application server. For Rails, there's a similar protocol called Unicorn. The cool thing about this, and the cool thing about using a framework to build your app, is that this app will work with an embedded server and an application server with just some slight configuration changes. Okay? If you were to actually write your app without using Django or Rails, you probably would have embedded too deep in your application details about the HTTP server. It's going to be hard to hoist it out. But now you can. We'll talk a lot more about these. But let me show you the difference in just my simple app. So I actually, once I learned that it takes 3 seconds, I actually always have an Nginx installed on my local machine. And my Nginx listens on port 8008 and has a very small configuration file that says all the static files serve directly and everything else forward to port 8000, where my embedded server sits. So I'm still using the embedded server for Django for serving the views, but I'm putting Nginx in front of it to take care of all of the static files. Seems like such a trivial thing. 218 milliseconds. Okay? And this is just the simplest page that you can have. Forget when you have pages with lots of assets. Okay? It makes a big difference. And so this is how I'm running my automated test. And from 3 seconds to 200 milliseconds, big difference. Any questions? Yes?
Just change the server from local to
what I did actually, I just changed the port number there.
right.
But this is misleading. Okay? First, I actually spent time installing Nginx on my laptop, and it's always on and running for my development. Installing UWSGI, which is the application server, and configuring my app to, writing the configuration. So let me talk a little bit more about this, because this is this looks like a small change, but it's actually not. Now I have actually 2 processes running on my machine. So I have Nginx, and Nginx is actually a pretty big beast. The first time you learn about it, you have to read how to install it. Installation is easy, but configuring it, it's not trivial. Okay, it's going to take you an hour to read it, but it's one of the greatest pieces of software that are used around in web services. It's worth that hour. For this part, it's even somewhat harder. I don't know the story about Unicorn on Rails, but UWSGI, which I picked for my application, has so many configuration options that it'll take me to the end of my career to use them all up. So to get started with it, it'll probably take you another hour to install it. Installing again, it's easy. You just install the package, but configuring it, write a configuration file. Both of these are daemons that have to be up all the time on your machine. They need start, stop scripts, and all that fun stuff. So if it's the first time you've set up a daemon on your machine, it may take you maybe more than an hour. But this is actually a very worthwhile investment. Any questions? Okay. So I think this step you should even take if you're a 1-person developer before you even think about scaling. Okay. Furthermore, as you will see later in this talk, these 2 pieces, this is just the beginning of what they can do for you. Okay? we'll be using them in the rest of our story a lot more. And so let's move on now. The first issue I'm going to attack is responsiveness. Even before I go to many users, I want one user to have a good experience. And this is not so easy, necessarily. So what you have to worry is how long does it take to your site to respond? And we see that my app running locally responds with the first page in 200 milliseconds. This is after you've taken care of all the static files and such. Generally, I've seen studies around that say under 2 seconds, people will generally come back. More than 2 seconds, they'll perceive it as slow, maybe not worried. There are these very interesting and surprising measurements from Amazon. They say that if they increase their response time by 100 milliseconds, they lose 1% of their sales, which is big money. And you think, how could that be? Which human would give up in 100 milliseconds when they want to go buy something? Well, of course, not every individual would give up, but statistically, that's kind of the rate at which they lose revenue with increasing latency. 500 milliseconds of latency costs Google 20% drop in traffic. These numbers are what I could find. I'm sure these companies have much more accurate numbers internally, but it matters. Okay, time is money.
Wait, what do you mean by drop in traffic? Just don't go back to go on Bing or what?
You're talking about Google?
Yeah.
Yeah, I think people don't come back. They maybe go to Bing. Okay, surprising, right? I mean, I don't know how to use Bing, but it matters. And by the way, I didn't even put it here. If you work for a financial firm doing high-frequency trading, those people care about the speed of light. They want to locate their servers close to the exchange. Okay, that's how much they care about latency. They don't want a server that's 2 blocks away from Wall Street. They want it on Wall Street because they worry about the time the electrons take on the wire. That's crazy. Okay, and I'm not going to teach you how to fix that because what we're going to be looking at is this kind of numbers. What does this mean? The app, by design, cannot do anything that is not either very quick to compute or it's already computed and stored in the database. The most the app should be asked to do to respond to a request is go fetch 1 to a handful of things from the database and then package it together, construct the template, and send it back. Anything more than this, you're going to take longer than you should to respond back. For example, imagine that when you click a like button in Facebook, the response comes back to you saying, okay, I got it. But this like is most likely not reflected on everybody else's web pages. That's going to be done later. Okay? Because they want to respond to you, give you the impression that the site is quick, even though it hasn't finished what it has to do. This is something very important. The framework won't actually do this for you. You have to design your app with this in mind. It's very hard to change it later if you make your app do complicated stuff in the process of responding. So the techniques that you use here are 2 main ones. One is deferred jobs, and one is caching. How many of you are using deferred jobs in your project? You're using Celery, right? And anybody else? That's normal. It's normal. That's how I did in my first 2 web services, because I only had 2 users. But let's see, how would you use deferred jobs? This is really cool stuff. So the way this works is for every request that comes in, every view, you think, okay, what do I need to do to respond? And then, is there any other work that needs to be done on behalf of this request? And if there is, we're going to use a separate database called the task queue. And the application will be written to kind of file work items, package a work item and put it in this task queue to be done later, and then immediately respond. This is very important. The application responds before it finishes all the work. All it has to finish is the work that needs to be reflected on the page. If you need to compute something to show on the page, you have to do that. Then you send the page. If there's other work to be done behind the scenes, you're going to defer it to later. Okay? Now, how do you actually do this? Well, once you do this, of course, you have to take care of this work. So we're going to have a separate part of our application. Take care of taking these items off the queue and processing them one at a time. Imagine that you click the like button. A web request is sent to the web server. The web server records what do you like, who are you, what is the time of the day, puts that all into a little data structure and puts in this database and responds OK to you. Okay? And you think you're done. Then a few milliseconds later, or perhaps a minute later, whenever, depending how busy this is, it's going to take that packet off from the database. You're going to say, OK, which is the item being liked? Let's go and update counters in the database and so on, construct reports and all that. So once you take a step to actually build this into your application, it's going to enable, you're going to feel the kind of freedom to do so much more stuff with your application that you couldn't do before because you always were under pressure. So this thing is going to do cleanup work. So for me, there's a timer that goes, every 5 minutes, it goes and fetches some stuff from another database, prepares it. Once a day at night, goes and cleans up the databases with stale stuff. You can do so much work with this time. Excuse because you're not slowing down the web server. The question is, how do you actually do this? It's easy to draw pictures, but is it easy to actually write the code for this? The good thing is that there are libraries ready to use that take care of most of this stuff. You just have to decide what is it that you want to be done later. And the application, the library will take care of constructing this blob, putting it into a task queue, running these workers, getting stuff off the task queue, and running the work. Okay? Yes?
Would there be race conditions between the application server and the...
That's a very, very good question. Would there be a race condition? And I assume you would think about database. Yes. I should have pointed out that typically these task queues, the way they record their work is in the database. They write something in the database. They increment the life counter. They don't have an opportunity to change the page that the user is seeing anymore. That's gone. That response has gone back to the user. The only thing you can do, record something for later. Yes, there could be race conditions, but you always have to write your application assuming that anybody can write to this database. You can have multiple copies of your application servers writing to the database. So in some way, if you design this properly, it doesn't make a difference whether there are many of these or many of these or many of the two together. It's just many people writing to the database. I want to show you, okay, so much of this lecture is going to be an overview of techniques and tricks, but there's two parts where I want to go a little bit in detail and actually teach you exactly how it's done. And I'll do it in the context of this library that's very commonly used for deferred tasks in Python. It's called Celery. And it's very nicely integrated with Django, but you can use it for other applications, not just Django. So you have to import Celery. You have to install Celery. That's actually fairly easy. You have to import Celery. And then imagine that this is the view function that is supposed to take in a request, do some quick calculation, and return a response. However, let's say that this is a like request. You want to delay certain part of work. You take that work, that long task, and you create a separate function to do the expensive work. Okay? And all you have to do is to just say long task.delay and then pass in the data. This looks almost like invoking long task on the data. And if you did that, this view would immediately jump and execute this code. And will wait until this code is done and come back. If you write a delay, it means don't do it right now. Construct one of these tasks that say, I want to run long task with these parameters, put it on a database, and move on immediately. And respond to the user. The user is very happy. The application is very responsive. And then you have to write kind of this little annotation that says this is not a random method. This is a task. So go watch the database of tasks, and when you see a request for long task, then take that request out, unpack the data and whatever arguments this has, and invoke this method. Okay? And then this method would most likely write something to the database. There's no point in returning anything here typically, because, or if you do, this return value will never be used by this, right? Because this has already returned and moved on and responded. This is gone. So there's no point in returning values from here. Do you get this? Is this clear? Have any questions? So those of you who use Celery, there's a little bit more to using Celery than this. What is there?
So sometimes it doesn't actually serialize things properly, and it gives you errors that make no sense.
Sometimes it doesn't serialize things. I never had that problem. Oh, I did. With some binary data?
It has to do with not being able to find some class definitions.
Yes. So you have to configure Celery to actually tell it where to find these methods, because imagine what Celery does. It goes in a database and finds the name long task there. Well, which long task from your big application? So you have to configure it. The other thing that you have to do is, I'll go back to the previous slide. You have to run another daemon on your machine, which is this kind of long-running application that keeps pulling tasks from the queue. So now your little application has at least 3 processes running. The web server, the application server, in which is your Django or Rails app, and another one just like that, except with a different wrapper on top. That's the task worker server. Okay? So there's more moving parts, more things to monitor, more things to go wrong, more things to die.
Are you not counting the task queue server or the database server in this?
I'm not counting the database server. Yes, the task queue server. Okay, so Celery can be configured to store the tasks in the database, or in some other database, perhaps, if you so wish. But it could use the same database, just the special tables. Yes.
Yeah. It's like, so you know how like for long tasks it writes to the database later. So how about if like the client does something that relies on that write to the database, but that hasn't happened yet?
You have to design your application such that that's never needed.
Okay.
You have to design the application assuming that. So I'll move on. This happens right away. This you don't know when it happens. It could happen immediately. Okay? You have to think what happens if the user comes back and doesn't find the request, and that's a matter of design. You have to worry about that.
So like what examples would this be useful for? And like I guess just some examples you could give us.
The thing is, once you start using it, I have tens of these in my application. But I guess before you first use it, what would you do? So for example, in this touchstone application that I showed a page, I get in the request, and I want to respond very quickly, but there's a lot of computation. I need to put this request in the history of requests and compute fairly sophisticated state of the video client. I mean, is it buffering? How long has it been buffering? Do I need to send emails, alerts that it's been going bad for too long? Like sending alerts, right? You need to send an email. You're not going to send an email here. You're going to defer that, and the email is going to be sent a few seconds later. I have a lot of cleanup, a lot of caching management that's done following a request, but not right away. So it's deferred. The people who use Celery, what else do you use it for?
We're primarily using it to send emails, and then if someone doesn't reply, to send another email later. So we have to come back at some later time and check the database.
That's actually a very good point. You can never do that with a request. The user makes a request, you respond, it's gone. If you need to periodically do something following that request, this is the only way to do it. Okay, moving on. So this was deferred task queues. Very, very cool stuff. Very useful. let's move on. We're still trying to make this fast. The only thing we've done so far is we've thought, what do we need to do in our web app, and we separated out the stuff that can be done a few seconds later and the stuff that has to be done now. But even then, your application will still be right into the database. Databases turn out to be one of the biggest obstacles to savings. They are actually slow because they have very stringent requirements on consistency and transactions, and databases are designed such that if the power goes away, stuff is saved. It's on the disk. So because of this, they have to constantly use the disk. Disks are slow. But the good thing is that most applications are very read intensive, not so much write intensive. Remember from last lecture when Faisal was talking at Conviva, we had designed an application that actually was doing a lot of writes in one of the tables. That turned out to be a bad design. We suffered in many ways from that. It gave just some stories. So if your response depends on many database reads, the response will be slow. My previous web service application, not this one, it was taking 5 seconds to generate a page. Okay? And because to generate that page, I needed to make many queries to the database. Each one would take 100 to 100 milliseconds, but it all adds up. I've just tested it now, that application, and it actually takes well over 10 seconds to generate the first page. That's, I mean, people give up. Even people who like you will give up 10 seconds. So perhaps we can reuse the response because maybe you don't need to recompute this page every time. The login page looks mostly the same for everybody. Maybe the portions of your page change very rarely. Maybe the whole page, there's some change always, but there's portions that don't change, like the ads. They don't change very often. You don't need to change the ad every second. Or the messages in your Facebook page change rarely. We're going to be using caches. And the first cache that you have, and you don't have to do anything about it except know it exists and a little bit how to use it, it's the browser cache. Everybody who's going to be accessing your application has a browser cache in their browser. And this is your stuff here. Okay, and this is the browser. So I just want to tell you a couple of things about how you manage browsers. So imagine at 9 a.m., somebody tells the browser to load the URL. The browser will immediately talk to the cache that it has, and if it finds that the URL is not in the cache, it will actually send the request over the net to the server. And let's say that the server has its own cache in front of your Rails app. This cache will immediately see, well, I don't have URL, so it will invoke the view in your application. And the one thing that the view does, it computes the page, and it also adds to it this indication that this page is good for 2 hours. I won't be changing this page in 2 hours. This cache that's in front of your application remembers the page and remembers this expiration. And the HTTP protocol has mechanisms in its headers to communicate this to caches upstream. And this could be the browser cache, or your ISP may have caches in between. So there's a cache control, there's an expires headers, and you don't normally need to know exactly the precise specification for it, because typically your framework will have ways to say this view expires in 2 hours, and then everything else will work. So the browser gets this request, it stores it in a cache with this expiration age. Somebody comes in an hour later at 10 a.m., and the request will be in the browser cache. But most browser caches, depending on how the cache is being controlled, will still verify whether this page has been updated. So even though it's in the cache, it will send a request to the server with this header saying, give me the URL if it has been modified since 9 a.m. because I have the 9 a.m. copy already. And this cache that's in front of your Rails app can immediately say, actually, it hasn't been changed since 9 a.m. So it responds very quickly, and with this is a response that's empty, so it's very small, it's very fast. and there's a special status code 304 not modified that tells the browser and the browser cache, okay, you can go ahead, the copy that you have is actually fresh. So this is like the best of both worlds because you cache the stuff and you can put a fairly long expiration age because you know you'll be contacted if somehow the page has been updated. Okay? And then at 11 a.m., without any action from the outside, the cache will expire the entry because it was downloaded at 9 a.m. and it has a maximum age of 2 hours. So next time somebody comes, it will just go back to the server again.
But this model is only applicable to static pages, right?
It's definitely applicable to static pages, and then you put a very, very long expiration age. But it's very applicable to dynamic pages. Will your login page, like my login page never changes. It's generated dynamically because, maybe I could have a static version of it, but it's so much easier to make it dynamic. So even dynamic pages actually can be cached. And we're going to be doing a lot of this in the next few minutes.
So would that include like dynamic, like even the JavaScripts for the page?
JavaScripts are static assets. But by the way, JavaScripts, remember, we already served them through Nginx. Nginx takes care of all of this stuff. Based on the file modification date, it does all this cache negotiation with the browser. So magically, things will just happen for you. You don't have to worry about that. The moment you update the file on the file system, Nginx will notice and will immediately expire the page. If somebody ever asks, we'll actually send the page back as opposed to not modifying. And when I did the demo before for you, I had to turn off the caches because if I didn't, even my slow embedded server would be very fast because it would be full of 304 responses. So that's an optimization. Let me see if I can demo this to you a little bit. I have another page. This is my previous web app. This is a continuous integration server that I wrote for Conviva. Each one of these blobs is a branch. These are all the recent commits. And this automatically checks out of Git the whole code base. It takes about 40 minutes to build, and it runs 3,000 tests on it on a cluster of 100 machines, including Macs, Windows, iPhones, Android TVs, and all that. So it's a pretty big system. And if I refresh the page, I have to probably lost my VPN. Okay, it's fairly fast. Okay, say, wow, George did a pretty good job. And look how many branches we have in flight. These are all of our trains, 283, I don't know why we have so many. Anyway, people abuse this system. This is the trunk with a lot of commits even today. And to build one of these pages, there's a lot of queries. I have a query for the commits with the dates and usernames, all of these builds on different machines, all of this data that tells me how many tests have been failing. So we have 18 failing tests, and you can see that here there were 11. So these magenta things means they started, 2 more started to fail here. There's a lot of stuff, okay? So if I go, this is another page. Let me refresh this to make sure it's, okay, so these are, by the way, if you're talking about deferred tasks, these are all the daemons that are running currently. And because these tests take a while to run, right? So, and these are cleanup tests anyway. But what I wanted to show you is cache management. Let me actually expire all the caches forcefully. So I built this just to be able to test my application. And this is what, unless somebody from Conviva, this is how my application really behaves if you don't have caches. It's still working. It hasn't loaded. It says waiting. So if you don't have caches, this is the experience that your users have. It's now up. And what it has done, it has actually computed all of these tables and stored each one in the cache. And if I refresh that, it's a couple of seconds. And that's not because suddenly the computer computes faster, it's because I stored this. So let's take a very short break because today I have to finish early so that we can do the course evaluations, okay? And then we move on. I have a lot more cool stuff to show. When I discovered that, when I had that idea of using caches, it was such a liberating thing because suddenly I can hide from my coworkers more and more work that I wanted to do to construct that page. So it essentially allowed me to make the application even more sophisticated, construct even more information because I know I would not be affecting users more often. But that's not what browser caches that I showed you there, unfortunately. Browser caches are not enough for that. Browser caches are not enough for many reasons. One is they only work for one client at a time. Every single client gets a better experience the first time they suffer, after the first time they suffer. Okay? That's not good enough. Some browsers have too small caches, and some browsers have slight differences in which they process those cache control headers. So you cannot have 100% guarantees that you have a good experience for all browsers. But more and more important, and this is a lesson that you really have to learn. If you want to build a solid web service, you cannot do it by relying on client-side mechanisms. You cannot rely on the client to ensure the performance, the security, or any other guarantees that you want to give from your web service. Because for one thing, the bad guys control their clients. So security, you cannot rely on the client. You have to ensure security at the back end. Again, for performance, you can have a lot of people hitting your website and perhaps maliciously, and it takes the website down. So you have to really bring into the server all the mechanisms that you need to ensure everything you want to ensure. The first thing you do is you put a cache not at the browser, but at the server in front of your server, such that everybody hitting that page, no matter from what browser, they get a benefit of the cache. Right? So you put another component, and now I'm starting to drop from the bottom because I can't fit all the components I told you about. Normally you'd have them all at once. Okay? So you start another component, which is called a reverse proxy cache. That's a complicated name. It's really a caching proxy. It sits in front of your web server, and it will. It knows how to do one thing only: is find if something is in the cache, check the expiration time. If it hasn't passed, serve it very fast. Only if that's not the case, it will then go to the web server. So here, I'm not going to tell you many details. I'm just going to mention some names. If you've heard of Squid and Varnish, these are two pieces of software that do caching ahead of web servers. There's another way to do it that's similar in concept but different in execution. You buy a service from a company that's called the Content Delivery Network. Akamai is the best known example of that. And what this company will do, they have these caching proxies all over the world. For example, Microsoft has a contract with Akamai. And Akamai will take the homepage of Microsoft from the Microsoft web server and replicate it in these caches all over the world. And when somebody from Indonesia types Microsoft.com, they actually don't go to Microsoft, they go to Akamai, some computer in Indonesia. And Akamai most often will have the Microsoft web page, and you'll feel like, wow, Microsoft is in Indonesia. And only when they start doing more sophisticated stuff, this cache goes and actually talks to the real, this is called origin server, in that case. Okay? That's what's
I think nowadays you don't really have to pay. You can just use Cloudflare.
Cloudflare?
Cloudflare. It's a free service, and it's just as good as the paid ones. It's just when you use a large amount, then you
Yeah, so whenever I hear of something that's free and just as good as a large one, I become suspicious. the truth is, some of this stuff is free, but the moment you go to millions of users, you have to be ready to pay some money. Because everything that's free, it has a gotcha. Unless it's a free software that you install and manage yourself, like Nginx, Apache, Squid, Varnish, that's okay. But these companies are essentially, Akamai charges is the premium provider of this. Okay, so there's not much you need to do for this except understand how caches work, and they work conceptually like the browser cache. So you have to do things like think, okay, should this be a GET? When you design my application, should this be a GET request and therefore cacheable, perhaps, or a POST request? POST requests are never cached by anybody. Browser caches, caching proxies, CDNs, nobody caches POSTs. So use GET whenever it makes sense. And think about what expiration headers make sense as well. Okay. However, even this is not enough. One problem with this is that this caches the whole page or nothing. What if you have a page like I had on my demo? My demo had a little portion of a page, one for each branch. The trunk gets many commits a day. 3 branches back, we only do hotfixes every other day. That's going to have a much better cache behavior. I don't want to cache the whole page because I'd be throwing up a lot of the page that doesn't change from day to day. Okay? So I want to be able to control the caching by portion. So I went and took screenshots of a Facebook page. And if you realize, this is built out of components. This part here, it depends on your profile. Whenever you change your profile, something will change here. This part here is ads. Okay? Maybe many users can reuse this part. It's not specifically just for you. This part here changes whenever you get a new message. Haven't gotten the message, you can reuse this part even though the ads change. And this one is about your friends. Okay? So when you design your app, you have to think about caching. What makes sense? What level of granularity you do caching? If you want to do this kind of trick, you cannot rely on CDNs, caching proxies, browser cache, because they just cache the whole thing. So how can you do this? And this is the second cool technique I'm going to teach you. Memcached. Anybody using Memcached in their project? Oh, no, but by the time of the demo, you'll have so many hits on your software that you'll wish you used caches. Okay? So what is Memcached? Memcached is yet another process. All of these things like to be in their own separate processes. And you talk to it over a socket using client libraries. So don't really open the socket connections. The client library does it for you. And it really feels like a hash table. It has get, set, and delete. Except it's a cache, it's a hash table that's shared by all of your application servers. Okay? So let me teach you some tricks of how to use Memcached effectively. So you can cache various things. You can cache results of individual computation. Perhaps you need to factorize a prime number in your application. I don't know why you do that, but let's say you need to do that. You may want to cache the result. Just like you'd cache it in a hash table in memory, you cache it using Memcached. You have some expensive database queries. You can cache the query. The key would be the actual query string, and the cached value would be the output of that query. So that prevents you from going to the database again. Or you make several queries, and you render a fragment of your page. You can cache HTML. Or you can cache the entire page. But at that point, I mean, maybe you should let a Varnish or caching proxy do it. So the big decision here for you is to decide what to cache. You should cache stuff that is expensive to compute and changes relatively rarely. So for everything that you cache, you pick a key. Traditionally, keys in Memcached use this colon, but generally any string would work. And the idea is that if you ask Memcached for this key, and if somebody has stored that key in the Memcached, you'll get it back. So this is how it works. This is your application code. This is Memcached D, and this is your database. Somebody says, get friends George, and you do some computation, and you say, well, maybe I already computed this, so you call this Memcached get. This is a library that you use. This talks to the Memcached D server, which has all this stuff in memory, it's very fast, and it comes back and says, I don't have this. Well, then I have to do the database query. I go to the database. This takes a while, okay, compared to the Memcached, much slower. And it comes back with the response, and you immediately put the response in Memcached. So you have 3 network round trips to process on your machine, but this is the only one that really matters. Because next time somebody wants get friends of George, you go to Memcached first, as before. Memcached says I have it, and then you can bypass the database query, and this can be faster. So this is actually what you've seen in my demo. I use Memcached for each of those tables. This can make a big difference. So imagine that you have a simple SQL queries. And it's simple, not only simple, but you've just done it recently. So it's in the MySQL cache. The database itself has a cache. You can do about 6,000 of these per second. Memcached can do 10,000 lookups a second. Okay? Well, because Memcached doesn't use disk, it's in memory. Also, Memcached doesn't have, it's very important, it doesn't have any persistency requirements. If Memcached, if the machine loses power, you lose everything in Memcached. So it's a cache. It's not a storage where you store important data. If your simple database query, it's not in the cache, MySQL will run about 2,000 a second, Memcached 10,000 a second, because for it, it's the same work. If it's a complex DB query, 100 a second. Here you do 100 times faster. And if, like I have in my application, it's a render HTML based on several complex queries, you do maybe 5 seconds per computation. This guy does it in the same microsecond level time. Okay? So this is what you've seen. You've seen an example of this. 5 requests to Memcached to load those 5 tables and serve it back, as opposed to computing it everything from scratch. Any questions? Yes. Oh, yes.
What if you want to distribute your cache? Does it split that?
Memcached is distributed. Yes. Facebook has about 10,000 of those machines, all making one big cache. And you don't need to talk. You don't need to think about it. You just say, get friends George, and the system will figure out on which of the 10,000 machines and whose memory the cache is, if it's at all. The nice thing is that install a library, install Memcached, it does all this for you. Okay, so here's a little wrinkle with Memcached. Let's say that now you want to update the cache. So you can, well, you set the cache using this Memcached set. You give the key and some text. It could be HTML, output of MySQL, whatever. What if somehow I change the friends of George? You add a friend. Well, there are 2 possibilities here. One that you might not think of as the first one to use is to set an expiration time for each entry in the cache. This is actually the recommended way of using Memcached. You tell Memcached that set these friends of George for an hour. And after an hour, automatically just flush it from the cache. Okay? So if you pick a long expiration time, it'll maximize your cache effectiveness. But you may lose freshness, right? The other way to do it is what you might think of the more natural way to do it. Whenever the friends change, you recompute a set of friends and you set the new set of friends. Or you simply delete explicitly from the cache such that next time somebody goes, we'll find it's not in the cache, we'll recompute it and put it in the cache. The problem is Memcached has very few guarantees. It's not a database. It's not true that if you store something in the Memcached, it's there next time you go. Many reasons. First, Memcached is all in memory. If the machine needs to be restarted, it loses everything. Second, because everything is in memory, it has limited capacity. If you fill it up, it'll throw something out from memory. And third, when you use it in cluster mode, these 10,000 Memcaches that communicate, they have a simple and cheap communication mechanism, which is not guaranteed to not lose messages. So when you use Memcached, it's an optimization. You do not rely on it. You don't store in there your bank account information. And all this is so that it can be really so fast. All this is taken advantage of to make it fast. Okay, now here's where the animals come in with Memcached. So this is seems complicated, but it's not. It's just the same scenario from before, just replicated a bit. So get friends George is the task you need to do. You go and ask Memcached, and it's red because it's a cache miss. So Memcached replies, I don't have it. Then you go to the database, and it's red because going to the database is expensive. It takes 2 seconds, comes back and gives you the set of friends from George, and you immediately stick it into Memcached for an hour. And now you think, I'm in good shape for an hour. Anybody who comes in the next hour will hit the Memcached and reply very fast. I don't need to actually hit my database. And after an hour, the poor unfortunate user who makes the request just then will miss the cache, will have to go to MySQL, get the result, and put it in cache. Okay? This is, imagine any, here I'm just caching the result of a MySQL query. In general, this could be any expensive computation that you're caching. Okay? Now here's what can happen. You build this, you go look at your database usage and say, wow, my database is not used very much. I can turn on the traffic. I can allow a lot more people to come in. Because they'll be hitting the cache, and this guy can do 10,000 a second. Okay? This guy can do 1 every 2 seconds. So you allow a lot of people through. And they come in, and for the first hour, everybody's happy. Everything works perfectly. When that hour hits, the first unfortunate person misses the cache, goes to the database, and takes 2 seconds to come back immediately afterwards. Okay, if you run it at 10,000 seconds, we're talking, 0.1 milliseconds later, somebody else comes in, and the same thing, misses the cache, goes to the database. Okay, what do you think happens?
DBAs get very sad.
Your DBAs don't matter anymore because the system collapses. So the database gets very sad, and then maybe the DBAs will yell at you. This is called the thundering herd. It's a common concept. It's a very common concept in distributed systems, and it bites you in strange ways because you're thinking, I just optimized. I put a cache in front. It must be better than before. But if you're not careful, your optimization breaks at the same time for everybody. Another kind of thundering herd is when you have a live event, like we explained for Conviva. Everybody watches the World Cup final at the same time. Everybody hits your system at the same time. So that's another thundering herd. Okay? So I'll just take a few more minutes because I see people from HKN here. How do you fix this? There are several ways to fix this. This is as before, except that when you store it in the cache with an expiration of 1 hour, immediately you set up a deferred task for 59 minutes later. This is your Celery queue. And then everybody who comes in hits the cache and is happy. And 1 minute before your cache expires, Celery, your deferred task, will say, oh, it's time to refresh the cache. So it goes to the database, takes 2 seconds to recompute, gets the result, and puts it in the cache with another resetting the expiration time. Such that if you do this carefully, at no time will anybody notice a speed up. Because essentially the only thing that hits the database is your deferred cache refresh task. Never the actual incoming users. This is very crucial. You should not let your scale, incoming scale, you should not let it reach this, because this is slow. You put all these layers to kind of catch a lot of the work ahead of time. Okay? This is very, very hard to do right, because you always learn this by mistake, unless you've taken this class. Okay? The way it happens is exactly, it's very counterintuitive. You just built an optimization, and then you scale the system counting on the optimization to be on. You always have to ask yourself, what happens if my optimization doesn't work at some point? And I let you think about what happens, for example, if Memcached goes down. Okay, you rely on it of taking all this traffic, but it's, the power could go off. What happens? Well, it's another thundering herd. How do you prevent that? Okay, and then it goes on and on. Your application becomes a lot cooler. So one more slide, and I'll wrap up. This I just wanted to put together what we've learned so far, trying to bring everything in one slide. We learned about browser caches, similar kind of whole page caches directly for the servers. We've learned how to use web servers to take care of the static requests and only ask your application servers for the important stuff. Application servers use Memcached for fine-grained caches, use task queues for everything that take a little bit longer, and then task workers to take care of that. So I have a few more slides in the slide deck. You're welcome to take a look at it. It's about how you scale this to more users. So far, all we made it really make it fast. And I'll stop here to give you time to fill in the evaluations. And I'll see you on Monday when we write the midterm. Okay? Any questions while I'm packing? Questions?
What were the two apps that you made?
One was the continuous integration and automated testing app, and the other is this Touchstone app, which is a replica of our entire backend that is used for by our customers for testing devices. It's kind of complicated.